We're on part 5 now of blood vessels, and page 705. We're doing the physiology of blood pressure and associated functions. We have here a diagram. We begin with the idea of exercise and the idea that we're increasing the activity of what's called the respiratory pump, as well as the muscular pump. And what they're trying to express to us by this terminology of pump is that we're actually moving blood distally through the venous system, which is filled with valves, and it prevents the retrograde flow. So as long as the muscles are squeezing the blood will always move forward. It will not move backwards because of the valves. So over here we have, even at night while you sleep, you're not exactly subject to walking or moving, but the fact that you're horizontal and you're not having any major challenges, hopefully you do sleep horizontally and not standing, then that means that the blood flow challenges are minimal with respect to gravity, and the respiratory system is adequate to create some venous return in the prone or supine position. We have the when we're walking and we're moving around, it's good during the day. When we have some epinephrine and some sympathetic tone to our body, to get up and have some walking and possibly other more, how would I say, vigorous or joyful activity, some exhilaration in the day, and that brings about a great deal of what we now are noting as venous return. With adequate venous return, we have an increase in end diastolic volume, which I described in a previous chapter as pulling the bow of a bow and arrow, so that the arrow goes with greater force and out toward a greater distance. And I'm bringing this line across here with a positive sign, and I'm noting we're going to get atrial natriuretic peptide, ANP. ANP is that molecule which turns off the cascade that we've referred to as renin, angiotensin, aldosterone. Everything that is attempting to increase peripheral resistance and increase blood pressure, this is going to turn it off, because the heart is basically saying, I thank you very much, I have now an increase in end diastolic volume, and I'm going to have a really good stroke volume. Okay, so there's the other part of cardiac output, of course, is heart rate. And we're going to have an increase in heart rate from all of this that I've just described, exercise. But let's take a look here at the drop in blood pressure and the idea that we have cardiac centers. Where are the cardiac centers? They're in the medulla. And we're regulating then, how shall I say, basal metabolic rate, partly in the hypothalamus, but also more specifically in the medulla for heart rate and heartbeat. Okay, so blood pressure is part of the goal here. If we have a decrease in parasympathetic activity, remember the vagus is that which is slowing the heart rate down. So if we reduce vagal tone, which is all about inhibitory postsynaptic potentials, then we can actually increase the heart rate, because the heart would like to go at 110, and the vagus is slowing it down to 70. Okay. Another detail here is that we'll get a greater sympathetic activity with a reduced blood pressure because the body is responding to its set points, and we get an outflow of epinephrine. So with adequate sleep and all of that, we wake up with the capacity to have a good flow of epinephrine. Of course, we improve the situation if we have some exercise in the morning upon awakening, and we have the increase in epinephrine, and we also have a concomitant increase in thyroxine. The epinephrine declines eventually, thyroxine not so much, and we sort of can stimulate our set points. Okay, so we have an increase in contractility, and we have the simultaneous increase in heart rate from the increased epinephrine. And then, of course, if we toggle down a little bit on the vagus, then we're going to be toggling down on the inhibition, and we're going to free up the heart to beat a little faster. So the heart rate plus the stroke volume increased due to venous return, increased venous return, where it's going to give us a increased cardiac output. Okay. So then we're going to be observing then that we're going to be having this sort of balance point here in terms of blood pressure. So we do have reflexes and we do have sensors. So let's take a look here at the sensors. We're going to be learning about the common carotid as it divides between internal and external. And that's in the neck region, right next to the trachea. You can feel a pulse right here. It's a very prominent pulse right between the sternocleidomastoid muscle and the trachea. If you place your finger there, as you go upward, higher up in the neck, we get to this dividing point, and there is a sensor right here. It's referred to as the carotid sinus, and it senses blood pressure. In the aorta, there's an aortic sinus in the aortic arch. Okay, who operates these? What cranial nerves operate this? And we learned that the cranial nerve number 9, glossopharyngeal nerve, operates this one right here, the carotid sinus, whereas the one in the aortic arch is operated by cranial nerve 10, the vagus. So the vagus actually retains its full structure before turning into plexus. It retains its full structure all the way down to the aortic arch. So it is a single, clear, large nerve that you can identify easily when we take a look at the cadaver. Okay, so cranial nerve 10 at the aortic arch, cranial nerve 9 at the carotid sinus, and we sense what's going on here, a change in the balance. The hypothalamus then is going to respond. Ultimately, the medulla is going to make certain adjustments, and we're going to be able to change the vasoconstriction and the peripheral resistance, and then maintain blood pressure in a normal range. Okay, so that would be based on the stimulus of increased blood pressure. We can do the same thing when the blood pressure decreases. Again, we go to the carotid sinus and or to the aortic arch. Cranial nerve 9 and 10 will sense that change. The hypothalamus, in conjunction with the medulla, will make adjustments to the low blood pressure, and we'll get an adjustment to an increase in metabolic rate, an increase in sympathetic tone, and ultimately changes in heart rate and in venous return, and we get the good cardiac output that would cause us to have the release of ANP. Okay, so that's just the way you like that. Here's a much bigger overview on page 708. And on this page, we're noticing that we're going to be having the opportunity to make all these adjustments. What's being said here by these diagrams, by the way, is that the kidney and the heart have a relationship to each other. The kidney really requires significant blood pressure in order to filter properly and then to recover through ADH the water that is being filtered. Okay, so that's an important detail. The arterial pressure here inhibits baroreceptors, increases sympathetic nervous activity. We're going to get a renin release. The renin release is going to activate angiotensin to angiotensin 1. Angiotensin 2 will pass by the lungs and get activated by ACE1, not to be confused with ACE2 right now, which does the opposite of ACE1. I should bring that to your attention because we have the SARS-2 virus causing the COVID-19 illness, and it it binds to ACE2 to enter cells. This is ACE1. This is something that activates angiotensin 2, whereas ACE2 is a cell receptor that actually turns off the effects of angiotensin. We'll come back to this table in just a moment.